the theme of the question. Did we cover all the cases? We did. We covered all the cases in the restricted universe, okay, that we conditioned on. The game was what we actually played, right? Max picked B and A was opened, okay? So if we looked at all the cases and we looked at, there's two of them, then we indeed did the right thing. Looking at all the cases holistically might also be a thing you can do. I wanted to use conditioning, okay, and I think you need to get some practice using conditioning, so that's why I did it this way. But can you analyze it without using conditioning? You sure can, okay. So let's just quickly go through all the cases where it's right to switch, and we can just go down the probability tree and pick them out. Okay, so any case where you don't pick the door that has the prize in it right away, you win by switching. Okay, so if it goes A, B, you switch. That's the one that you want. Okay, so if you A and C is if it's behind A, C is picked, B is opened, you switch. Okay, same thing. Anytime you pick not the correct door, okay, there's another 1/9, there's another 9th, and there's another 9th. Okay, so all of those cases are good cases. Okay, so if you wanted to analyze this without conditioning, you can do it. But it wasn't exactly what I wanted to do. But so many of you asked, and I know there's so many different ways to solve a problem. So I'm just going to offer the alternate solution for you. Okay, that you can add up all of these outcomes, these 6 outcomes, where it's right to switch in those games. Okay, so it wasn't the game that we played. But there were different possibilities off the get-go, okay? So if it's behind A, Max picks B, and C is opened, okay? And there are 6 different permutations of this. So A, B, C, A, C, B is the next one. B, A, C is the next one. B, C, A, C, A, B. And the last one is C, B. Okay, all of them have a probability of a 9th. I don't know that it's worth writing a 9th time, plus a 9th plus 9. Okay, so the probability of E when you add it all up is 6/9 or 2/3. Okay, so you can add up all the cases and all the possible permutations of the universe, and you'll get the same result without conditioning. Okay, so it does work. Hopefully that's convincing. Anyway, other odds and ends, okay, other odds and ends. We were dealing with some conditioning rules. I don't want to review all of them, but the main theme was that if the rule worked based on set theory, okay, so if A and B are somehow connected and there is a result from, axiomatic probability theory, okay, like A is a subset of B, therefore the probability of A is less than or equal to the probability of B, then the conditioning rule should, or conditions for both on the same set, it should also work. Okay, so the general theme is that you should condition on the same set, the same event, across the board, but it should hold. Inclusion, exclusion holds, union bound holds, almost all the rules hold. But if you just have the probability of A equals the probability of B, yeah, the probabilities are related by equality or inequality, but if you condition, it might flip the other way, and you saw an example of that on assignment 1. You're asked to find counterexamples. Okay, but the other ones should work. Okay, so don't condition on different things. You probably won't get a good result that way. We talked about independence. We're going to talk a lot about independence going forward, but if the probability doesn't change with the extra information, those 2 events are independent. What is probability of A given B given C? That's kind of weird, right? These extra conditions, or certainly we're adding an extra condition C here, right? A given B given C. This is not like a standard notation. In fact, B and C are both sort of feel, at least the way I read it to you, both of them feel like conditions on A. Okay, so you might want to rewrite this. Okay, so this is not standard notation. If you want to have 2 conditions, you should just use intersection. Okay, so make B and C the condition. So use the probability of A given B intersects C. Okay, and the last bit here is a pretty important bit. If you knew the probability of A given B, could you find the probability of B given A? And if you unpack what the formulas are doing, let's just look at that. So the probability of A given B, that's the probability of the intersect of the 2 divided by the probability of B, okay, so taken as a fraction. And the probability of B given A equals the probability of B intersect A divided by the probability of A. And if you look, there's there's some term in common here, right? Something in common that we could substitute, okay? And indeed, the 2 things are related by that substitution, okay? They are connected, and it turns out that by a ratio of the probability of A and the probability of B. Okay, combining these 2 things together gives you what's known as Bayes' theorem. And that is largely going to be the subject of today, okay, is Bayes' theorem. Okay, so all of our example, and probably Friday as well. I don't think we're going to get through all of it today. Okay, but before we do, I just want to show you one interesting case of probabilities that are conditioned on things, on certain conditions, and drawing conclusions that you might not. They might have some strange just some strange results, maybe unexpected results. Okay, this is known as Simpson's paradox, and when something goes counterintuitive, sometimes we tag it as a paradox. And it has to do with sexism in the 70s. Okay, so we're talking about UC Berkeley's case of getting sued for sexism. They were not taking enough female students. Okay, so they got sued. Okay, so it was observed that 35% of female applicants were admitted versus 44% of their male counterparts. But when the university examined the data, they defended themselves and said, well, if you look at each individual program, we're actually taking more females than males on a percentage basis, which seems like that's kind of weird, right? It turns out both things were true. And as a case study, I'll just show you how the numbers can roll in both directions simultaneously using conditional probability. Okay, so let's imagine that UC Berkeley just had two departments, computer science and electrical engineering, and let A be the event that an applicant was admitted to their program of choice. Okay, so FCS is a female applying to computing, FEE is a female applying to electrical engineering, and similarly male and male for both CS and electrical engineering. Okay, the lawsuit was claiming, using conditional probability speak, okay, that a male candidate was more likely to be admitted than a female candidate. Okay, so we're saying that the probability of admittance given either male or male, okay, so either one, was greater than the probability of a given female for either one. Okay, so this obeys an inequality. And the university says, well, a female candidate was more likely to be admitted. Okay, so if you look at any individual department, okay, so the following would be true. Okay, so the probability of A, you're admitted given that you're a female applicant to, let's just start with CS, you're more likely to be admitted than an applicant that's male, CS, and the probability of getting admitted into electrical engineering as a woman was more likely than getting admitted as a male. Okay, so that might seem counterintuitive that both of these things can be true, but indeed you can derive numbers in tables, and it's not too hard to find an example where this is true. Okay, so let's take a look. Okay, so this is Simpson's paradox, named after Simpson, who first wrote about it. Okay, so both statements can be true, or if you look at the trends in the data, and this is a causal relationship or something we believe to be causal, they can switch. Okay, so they can reverse when you take them together. Okay, so let's look at the following data. So if in computer science, so the first one here, we compare the females' 33% acceptance rate, that's pretty easy to calculate, 33 out of 100. Males, 2 out of 9, which is 22%. Females in electrical engineering got in at a rate of 67%. Males, 46. Okay, so on a per department basis, females are getting accepted at a higher rate. But if you take them together, okay, and this is the entire table as a Venn diagram, all right? The blue bits are the stuff that show the acceptance rate. And we have 106 females over here, 37 of which were accepted. This is a 35% acceptance rate on this side of the table. And on this side we have, well, let's just add it up here, there's a 109 total, and 48 were accepted. This is 44%. Okay, so arguing about conditional probability can be tricky sometimes, and so the resolution of this is that women applied in larger numbers to more selective or exclusive programs than men did. Okay, and they did the opposite for engineering or CS was more selective, I believe. Okay, so, and vice versa for the more permissive program. Okay, and the reason that we would consider this to be a valid defense is that we sort of see the causal relationship between, looking at department by department sort of thing, right? Because that seems like a major thing that might influence your decision. Okay, it is possible to take this a little bit too far and be arbitrary and just say, decide this based on something more arbitrary, like the parity of the day of the month that they apply. Okay, which has nothing to do with anything to do with the department being permissive or exclusive or whatever. Okay, and it's very important that there be some sort of connection between these two things. Otherwise, we end up getting, situations like bias like this. You can get sued. In governmental terms, I know is a sort of a hot topic these days with elections being, having so much at stake. There is a way of rejigging zonal boundaries. Okay, especially in places like Canada, where they, you vote by district. Okay, so just redrawing the boundary can have huge effects. And you can often, redraw them in such a way that, liberal candidates get voted in majority conservative areas. You can have that happen. Okay, and it's the people who are in power who make those decisions. So this is known as gerrymandering, and it's got, it sort of smells like this. Okay, so just a little bit of a fun thing for you to think about, but definitely you should watch out for trends like this. All right, next thing today is Bayes' theorem. Bayes' theorem asks you to turn a conditional probability around. Okay, so if you're given, or the probability of event A given that B is true, can you compute the opposite, the probability that B occurs if you know that A has occurred? Okay, so 2 examples we will revisit in a moment. Color blindness. So the probability of color blindness in a male is 8%. Okay, so if male and probability of colorblind if male, so that would be 8%. Okay, so what is the probability of male if colorblind? Okay, and we actually were asked to do that problem early on. Same thing for the cancer test. Okay, so if you test positive, you know what the result is. Okay, so it's the probability is 90% correct. Okay, so what's the probability that the person actually has cancer given that they tested positive? So that sort of flips it the other way around. Okay, so we're going to use Bayes' theorem, which is actually just the substitution of those 2 formulas from the previous slide, and that is indeed the proof of this. Okay, so the probability of B given A equals the probability of A given B as an input multiplied by the ratio in their own probabilities. Okay, proof. Substitute the 2 things from before. I'm going to do a slightly different substitution just to save us a little bit of room. Okay, so probability of, sorry, I got this backwards. I want that one. So probability of B given A equals the probability of B intersection A divided by the probability of A. Okay, so this is just the definition of conditional probability. And we can substitute in for B intersect A using the multiplicative rule. Okay, so this is the probability of A given B times the probability of B. Okay, so to get here, this is the multiplicative rule. Okay, so there's nothing really to it. And, the person who discovered this, Bayes, also thought there was nothing to it. Bayes was a clergy, so it's told, that was interested in math, and there were many such people who were religious who were interested in math. He was interested in solving the problem of how many tickets to buy for a local raffle before it was likely that he would win. Okay, so he studied a lot of probability mechanics and came up with this theorem. He didn't think much of it, so he never published it. And it was only after his death that somebody looked at his diary, his math diary. I don't know exactly how that works, but and thought this was something worth publishing. So meanwhile, Laplace was also discovering stuff like this and publishing things that were deeper than this. He did a lot more exploration, but it's not named Laplace's theorem. It's named Bayes' theorem. Okay, so don't worry, Laplace has a happy ending. There's lots of things named after Laplace. So anyway, Bayes' theorem. Okay. We're going to revisit a couple of examples, the 2 that are here, first of all, and apply Bayes' theorem to it. I am going to reproduce the tree for you so that you don't have to. Okay, so let B be the event a random person is male, let A be the event a random person is colorblind. Okay, so the right-hand side of the tree here is male, so this is the probability of B, is this, right? The probability of A given B, the probability of colorblindness given male, is 0.08. That's here, right? That's the multiplicative rule. Okay, so you multiply those things together, you get male and colorblind. Now, when we did this problem before, I drew some circles around the relevant things, right? What were the relevant things? We're interested in colorblindness, which is A. Okay, so that's A and A. And we are interested in male. Okay, so male is here and here. Okay, and I drew some things around the sets, and we just looked at the events of interest and so on. But today we're going to use Bayes' theorem. Okay, so solution. We need to find the probability of B. We already found, find the probability of A, pardon me. We already found the probability of B. It's up here. And use Bayes' theorem. Okay, probability of A. Well, the probability of A is the sum of these two strands, right? These two events, right? You're either colorblind in female or colorblind in male, and you multiply these together, okay? So colorblind in female is 0.005 times 0.5, okay? So that's that strand, and colorblind in male is 0.08 times 0.5. You multiply all that out, you get 0.0425. Okay, so the probability of B given A is the probability of A given B times the probability of B divided by the probability of A. And we can just slam the numbers in. Okay, and when we slam the numbers in, we get probability A given B is 0.08. Probability of B is 0.5 divided by 0.0425. Okay, and that's 94%. Sorry for ruffling all the papers. I actually just wanted to go back and see. Get, I think we did this. I don't have it here. Yeah, so we did part of this. This bit here. Okay, this 0.425 is in the denominator. Oh. Doesn't matter. We have another one to do, so let's just quickly do that. But yeah, this number seems to match okay. Okay, so this was in the denominator before. Okay, probability of A. Cancer, we can do the same thing. Okay, so A is the event the person tests positive for cancer. B is the event that the person has cancer. Okay, so cancer here is on the left. And the probability of A given B is 0.9. Okay, so here and here. Okay, so again, we're going to use Bayes' theorem. Okay, so just a slightly different version than what we did before. But I have the cancer test slide out, but one comparison is enough. Okay, so the solution, I guess we need to find probability of A and apply Bayes' theorem. Okay, so the probability of A. Okay, so let's earmark A in this diagram real quick. Okay, so A is the event that tests positive for cancer. That's here and here. B is test positive for cancer. That's here and here. Sorry, yeah, B has cancer, pardon. Okay, so the probability of A, is the product, or sorry, the sum of these two strands. Okay, so we'll go down the left first, so 0.9 times 0.01. That's this left arm. And this strand here is 0.05 times 0.99. Okay, add all that up, and you get 0.0585. And then we use Bayes' theorem. Okay, so probability of B given A equals the probability of A given B times the probability of B divided by the probability of A. Okay, probability of A given B is 0.9, probability of B is 0.01, and then this denominator here is copied from above, and this is around 15%. And just to show you what we did before, okay, so this bit here, okay, we add all the strands together right in the fraction. Here we did it up here. Okay, here this is the multiplicative rule, okay, applied to that one strand. Okay, so we did it in the fraction. Okay, here we're doing it as two substituted things. But it ends up being the same. Okay, so the math is exactly the same. Okay, so Bayes' theorem allows you to talk about the backwards of things, right? And yeah, so the probability of A given B here is 90%. Probability that they test positive if they have cancer is 90%. But it's only 15% percent the other direction. I sort of went through why that makes sense when we did it. This one is interesting because maybe that's a little surprising that you can say the probability that you're male, given that you're colorblind, is 94%. Just think about it, right? Male colorblindness is 8% versus 0.5%. It's 16 times more likely in males than females. So you expect 16 out of 17 people to be male that are colorblind, right? It sort of makes sense. And 16 out of 17 is actually 94%. Makes sense. Okay, there's the other piece to Bayes' theorem. Usually the Bayes theorem that you tend to see, and we'll come back to the slide in a second. Okay, and it's called the law of total probability. Okay, so let's look at a collection of sets, B1, B2, all the way up to BK, that partition the sample space. Okay, so I've drawn it out here. I've drawn three pieces. They totally carve up S. Okay, so that means they're pairwise mutually exclusive. They don't overlap. And their union is the sample space. Then you can find the probability of A as the probability of A given B1 times the probability of B1, plus the probability of A given B2 times the probability of B2, and all the way down. Okay, and what does this all mean? Well, it's the fraction of where A overlaps each of these. Each of these things is actually a multiplicative rule in disguise. This is actually a probability of A intersect B1. If you look at the definition of the how the multiplicative rule works, this thing grinds down to that. This is the probability of A intersect B2. And all of these things, if you take them in unison, that's what this diagram shows, right? This is the bit that overlaps B1, the bit that overlaps B2, and the bit that overlaps B3. Now, why does this thing work? Well, you might have some intuition about it already, because this kind of looks like a weighted average. And indeed, when we're going through the different strands of the tree, we are taking a weighted average. But also, sometimes they call the collection B1 through BK the hypothesis. And why is it called the hypothesis? Because you can go through each case in turn, and you can say, well, what's the probability of A if B1 is, so case 1, B1 is, okay, well, if B1 happens, the probability is A given B1. Okay, well, you scale it up by multiplying it by B1's probability. Okay, that makes sense. And then what if B2 happens? Well, we can find the probability of A given B2, and then scale it up by the probability of B2, and so on. Okay, so each of these terms will give a certain weight depending on which of the cases B1 through BK happens. They can't simultaneously happen because they're disjoint, and one of them must happen because they are a partition. There's a special case, and we use this case a lot for Bayes' theorem. Okay, and that is the case that B occurs or B doesn't occur. Okay, so that's the hypothesis that's listed here. Okay, so the probability of A given B, probability A not B, given not B. Okay, so just to go back to this slide real quick, this here is a total probability calculation. Okay, why? Well, you went down one strand this way. Okay, so if female, right, or if male. Okay. This is another one. Okay, so the cases were if cancer, if not cancer. Okay, so this was a pardon me. This was a law of total probability. We weren't calling it that. It actually sort of felt like a weighted average of chance of cancer, weighted average of chance of color blindness. Okay, and that indeed sort of feels like what's going on. It is. Okay, let's do a longer example. Yeah. Okay, accident prone. So, do you believe you're accident prone? Do you have someone in your life that just seems to bump into walls and get in accidents all the time? It might be true. It might be true. Some people are clumsier than others. And an insurance company in this scenario thinks that they've nailed it. Okay, so there are people who are accident prone and people who are not. Accident prone people will have an accident in a fixed 1 year period with probability of 40% versus 20% for non-accident prone people. Okay, so if 30% of the population is accident prone, well, we're going to compute a bunch of things. Okay, so let's kick off by defining a few events. Okay, first event. Okay, let A be the event that a new policyholder has an accident. And the other thing here is the event that the customer is accident prone. Okay, let's work together on this one. Going through the problem, what are we given? Give me one thing we're given. Okay, yeah. Okay, so these ones here, you said are the probability of, okay, so let's see. The probability that a new policyholder will have an accident within a year is A. A given B. A given B is 0.4. Accident-prone people have accidents with a higher probability than A given not B, which is not accident-prone, is 0.2. Good. There are more. Give me another one. Okay. Probability of B is 0.3. 30% of the population is accident prone. Okay, we are asked what's the probability a new customer will have an accident within a year. And think about it, right? The customer is either going to be accident prone or not accident prone. And if they're accident prone, then this should scale by this much, right? 0.3 times 0.4. And if they're not accident prone, it should scale by 0.2. That feels like a weighted average, right? And I could draw the probability tree. I'm not doing that here, but you can imagine there are going to be 4 arms, and we would take 2 of those arms. Anyway, I want to use the law of total probability. Okay, so we have all the things, I think. The probability of A is what we're after, is the probability of A given B times the probability of B, plus the probability of A given not B times the probability of not B. Actually, we only got 3 of the 4 of these things. The one we're missing is probability of not B. How do we get that? Use the complement rule. Yeah. Okay, so this thing should be 0.7. It should come from here. Yeah. Okay, so it's in the problem essentially. Okay, so let's do it. So probability of A given B, 0.4. Probability of B is 0.3. Probability of A given B is 0.2. And probability of B complement is 0.7. Okay, add all those up. That's 0.12. That's 0.14. 0.26. And just as a sanity check, let's just make sure that we're not, losing our minds here. This sort of makes sense. It should be a number between 0.2 and 0.4, right? Because, the worst that you can get is 40%. The best you could get is 20%, apparently. And there should be, some weighting based on, is it 30% as close towards 0.4 as it is 0.2? I think it is, right? I think the difference here is 20% and 30% of that is 6%. Yeah, it seems to make sense. Okay, I haven't paused for questions in a while. Any questions about this? There's more to come, but yeah. Sure. Sorry, here. You mean the probability of A given B times the probability of B? Why is that not there? I mean, intuitively, if you look at this Venn diagram, the probability of A should be the union of these intersections, these 3 intersections, right? So it should be the probability of A intersect B1 plus the probability of A intersect B2 plus the probability of A intersect BK. I think you buy that probably, right? Down here, this is a bar, not an intersect, right? So if you want to connect to this intersect with this condition thing, a condition on B1, you have to scale it up by the chances that you're actually in that set. So these 2 things are different. Like you can, if you buy that this should be here, it's the probability of this given B1, which is going to be that, it's conditioned on that subset of the, you change the sample space. You have to scale it sort of down by the probability that you actually land there. Yeah. If you buy the weighted average calculation on this example, then you should buy out why this is here. Yeah. I don't know. I've given 3 different things. Maybe, I don't know. You don't look happy. You're happy? You don't look happy. I want you to be happy. Okay. Well, anyway, hopefully that works. All right. Thanks for that. Any other questions? Yeah. Okay. This is the sort of the crown jewel of today. All right. So you can combine these 2 things, and indeed, when you see Bayes' theorem written down, frequently it's written down as the combination where you substitute this in for this. Okay, and you write it, and this is just the 2-case hypothesis. Okay, so it's either in or it's not, but you end up getting this as the Bayes' theorem. Okay, and why does that make sense? Well, if you look at the Venn diagram over here, it is restricting your life to A, which makes sense. The probability of B given A. And it's taking the fraction of probability given that B is true. Okay, so it's on that side of the hypothesis. So it's the fraction. So you see the blue stuff on the top here. It is that portion of the total in the denominator, the total for A. Okay, so I'm just going to make that really clear by highlighting that. That is the fraction of the probability, that blue bit that's in there. The white bit is part of the total thing that's in A, but it is not the thing that we ultimately want to count. Okay, so we are going to use this on the next piece to this, and we have just enough time to get it done. Okay, but intuitively, when we did the very first example with the cancer test, we had that exact form on the denominator. Okay, so just go back and look for it. It looks exactly like this. Okay, but I want to do this one. Okay, so part B is suppose the new customer has an accident within the first year of purchasing their policy. Oh shoot, I lost all my givens here. Okay, so the probability of A given B is 0.4. The probability of A given B bar is 0.2. The probability of B is 0.3. Okay, so we're asked what's the chance that they're accident prone if they have an accident. Okay, so that's interesting, and maybe it's up to superstition, but if we actually believe that this model is working, we want the probability of B given A, and we can use Bayes' theorem. Okay, the big one. The probability of B given A equals the probability of A given B times the probability of B. Okay, so that's the piece that we want. And then the denominator is the law of total probability, both pieces. Okay, probability A given B, probability of B. Plus the chances that they're not accident prone. So this is probability A given B bar times the probability of B bar. Okay, so all these things just kind of drop into place in this final version here. Okay, so we can just, well, I guess we have the one other thing I mentioned, that's the probability of B bar is 0.7. Okay, so we have all the things we need. Okay, so I'll drop them in. 0.4 times 0.3. And then the denominator should be the same calculation we did on the previous page. Okay, so 0.4 times 0.3 is the same law of total probability calculation. So 0.2 times 0.7. Okay, so 0.12 divided by 0.26, which looks pretty close to 50%. It's almost a half, but it's just slightly less, 46%. Okay, so does this answer make sense? Notice I do this a lot, and does this answer make sense? I always think you should look at the answer and go, does it actually sort of hold water, right? Does it make sense? Originally, 30% of the population was assumed to be accident prone. You had an accident, okay, which is not very likely, less than 50% for the year. If you have an accident, you're more likely to be accident prone, right, than the original thing. That your 30% now has become 46%. So the extra information has re-estimated you to be more likely to be accident prone. Okay, not by a lot, but by a little bit. Yeah, so sort of makes sense. Okay, I have one more minute. Are there any questions about this first? We're going to do a couple more examples on Friday, I promise. Okay, well, I don't want to waste the minute. So I just want to point out, this calculation here on the cancer slide, the original one from 19, actually has the same form as this. Okay, so we were sort of doing this by looking at probability trees, and I could have drawn a probability tree for this as well, but we didn't need it once we had this nice snazzy formula. Okay, so notice that this is actually Bayes' theorem, but we didn't actually use Bayes' theorem. Okay, so kind of cool. Okay, that's it. We'll see you Friday.